In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranab is here to deliver today's presentation, Power Transformer Part 23. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with comprehensive guidance for selection of solid insulation. Power transformer is one of the most critical and expensive equipment for any power utility, and its age-related failures due to dielectric problems are reported to be as high as 75%. So, it is rather important to identify the deterioration stages of dielectrics as caused by the weakness of their structural bonding along with the decaying process of their degree of sensitivity towards aging. However, aging process of the dielectrics is also strongly dependent on certain variables such as temperature, oxygen and water levels in the transformer. By controlling all these variables, the life of transformers can be maximized. For the conventional transformers, the insulating materials comprising of cellulose type and would have been used to insulate the components such as conductor jackets, spacers, and barriers. Because of the low cost involvement, the cellulosic insulating materials are being preferred to use for restricting the temperature rise of the transformer internal components. Oil impregnated cellulosic paper insulation is of class A insulating material and can withstand temperature up to 105 degrees centigrade. Thermally upgraded insulating paper with a heat resistant temperature of 115 degrees centigrade is also available in the present market. However, transformer while configured with oil pigmented cellulosic paper insulation of thermal strength 105 degrees centigrade, and if somehow its operating temperature has gone up beyond 120 degrees centigrade, then the aging process of the existing insulating material would have been accelerated much faster due to have a poorer thermal strength. Aging process of the cellulose made solid insulators would have to accelerate while these insulators are experiencing a strong synergistic effect of three major components such as heat, water, and oxygen. Out of three, heat component which relates to temperature, and in presence of water, these two are more responsible to create a strong synergistic effect on the long chain of molecule structure of cellulosic insulators. During the operation of transformer, moisture is thus to be accumulated on the cellulosic insulating paper over the years. And as a result of its aging process, these long molecular chains are generally broken into several number of minute particles. Degree of uneven aging of cellulose insulation paper is mainly influenced by the moisture distribution of the paper as corresponds to temperature distribution. The physical and chemical properties of the cellulose insulation paper as would have been changed, causing a substantial loss of tensile strength of the paper and becomes brittle. However, the degree of cellulosic paper aging can be determined by the process of using cellulose polymerization degree. It has been exhibited that the moisture content of the cellulose paper, if has to increase by 0.5%, then in each occasion the degree of polymerization of the paper would have reduced to half. Considering that the temperature at the hotspot during short-term overload is usually over 120 degrees centigrade, the aging of the insulating materials is prevented by substituting Aramid insulators for conventional cellulose insulators, which ultimately increases the transformer capacity. Nomex fiber is a kind of synthetic fiber of high thermal endurance, and also its structural configuration is thus to be designed as aromatic polyamide or aramid, whose generic name is Nomex. Again, I repeat, Nomex fiber is a kind of synthetic fiber of high thermal endurance, and also its structural configuration is thus to be designated as aromatic polyamide or aramid, whose generic name is Nomex. Nomex, while employed as an insulation paper of synthetic base that offers high degree of thermal strength of 220 degrees centigrade, that is class C type of insulation, high inherent dielectric strength, mechanical toughness, flexibility, and resilience. Since ingredients of the Nomex insulations are so stable that even at the time of aging process, Nomex papers never produce water or toxic gas in transformer dielectric fluid. Nomex aramid paper demonstrates improved longevity, reliability, and thermal resistance in liquid immersed transformers as compared to both types of cellulosic insulation paper such as Kraft paper of temperature class 105 degrees centigrade and also of thermally upgraded Kraft paper of temperature class 115 degrees centigrade. Its superior physical and electrical characteristics are the ideal balance for using as an insulating material, especially in harsh and high temperature applications. Exceptional thermal stability, outstanding mechanical toughness, excellent specific insulation resistance, and inherent dielectric strength, unaffected by most solvents, highly resistant to attacks by acids and alkalis, excellent flame resistance. All such properties are ideally supplemented in Nomex aramid paper. Transformer, while configured with Nomex aramid paper insulation, would have to offer an increased reliability in emergency overloading, harmonic load heating, and voltage variation conditions, along with the reduction in life cycle cost. It is also to be exhibited that the electrical and mechanical properties are effectively retained for at least 10 years of continuous exposures at 220 degrees centigrade. So, Nomex paper gradation that has to be individually selected by analyzing the dielectric characteristics of the Nomex paper as corresponds to variation of temperature and frequency, and also has to assess its electrical characteristics in order to confirm its thickness as per fundamental design criteria of transformer, that is the rating capacity, the mode of application, the large range of temperature rise, trend to a frequency variations, load fluctuations, etc. Again, I repeat, Nomex paper gradation that has to be individually selected by analyzing the dielectric characteristics of the Nomex paper as corresponds to variation of temperature and frequency, and also has to assess its electrical characteristics in order to confirm its thickness as per fundamental design criteria of transformer, that is the rating capacity, the mode of application, the range of temperature rise, trend of frequency variations, load fluctuations, etc. Probable framework by physical configuration. In general, a liquid filled power transformer whose life expectancy is normally based on number of factors, and the most important of which is the quality of its insulation system over time of operation. It is quite evident that the aging rate of the cellulose insulation is directly affected by operating temperature, water, oxygen content, and contaminants, out of which oxygen ingression in transformer oil is of great concern, as it would have to accelerate the oxidation of the oil and at the same time has to intensify the aging process of its solid insulation, most importantly the Kraft paper within its windings. The oil used in power transformers is particularly susceptible to moisture, and its insulating property will be seriously affected when even small amount of moisture is present. In addition to this, the insulating quality of oil and its performance as a dielectric fluid can be drastically hampered due to oxidization as well. Again, I repeat, in addition to this, the insulating quality of oil and its performance as a dielectric fluid can be drastically hampered due to oxidation as well. Other than atmospheric oxygen, water also serves as a carrier of oxygen, and leaky gasket, if any, would have to implicate a real hazard for causing both oxidation and moisture contamination of the dielectric fluid. Oxidation has a specific outcome as the formation of acids in the insulating oil, which is in turn contributes to the formation of sludge. However, the rate of oxidation is directly linked with the rate of rise of temperature of the oil. So, higher be the oil temperature, faster will be the oxidative breakdown of the oil composition. Generally, transformer insulating oil has to work at temperature of 70 to 80 degrees centigrade and any ingress of oxygen, then with the temperature, viscous type of oxidation may have to take place, resulting formation of acids in the insulating oil, which in turn would have to contribute as the formation of sludge. The resistivity of transformer oil decreases with increasing acidity, causing a rapid destruction of cellulose insulating paper. The resistivity, that is specific resistance of transformer oil, should remain at the value of 35 into 10 to the power 12 ohm centimeter at 90 degrees centigrade and 1500 into 10 to the power 12 ohm centimeter at 27 degrees centigrade. And any deviation that would indicate that some defect has developed in the transformer insulation system. The increase of acidity simultaneously instigates further increase of dielectric dissipation factor, that is tan delta, of the transformer oil, which shows the increase of dielectric loss of the oil. However, the dielectric loss factor has to relate with the inability of molecules in the insulating fluid to reorient themselves with an alternating electric field. The reorientation ability of the molecules is totally dependent on the temperature of the fluid, the size of the molecules involved, their polarity, and the frequency of the alternating field. Again, I repeat, the reorientation ability of the molecules is totally dependent on the temperature of the fluid, size of the molecules involved, their polarity, and the frequency of the alternating field. It is further to be mentioned that the dissipation factor and the permittivity of the insulating fluid are also affected by the size of the molecules, overall molecular composition of the fluid, and relative orientation of functional groups within the molecules. In general, within a series of similar molecules, if the molecular weight increases, then the permittivity of the material would have to increase. In fact, factors such as moisture content, acidity, and oxygen content of the oil should therefore be dependent upon the breathing system of the transformer. Perfect monitoring of the breathing system and proper sealing against ambient air or moisture ingress thus have to be ensured so as to maximize the transformer's operational life expectancy. Since the oil in the transformer will expand and contract with temperature and load, a number of system design has been developed to help preserve the overall insulation quality of the transformer. Detailed statistics about the aging process of the organic materials are used in transformer should have been classified for thorough investigation and essential failure analysis for ascertaining the root cause of the fault so that necessary remedial activities can be taken up at the earliest. Having a larger database with failure data analysis may have also intended to determine appropriate corrective and preventive actions for restricting the repetitive occurrence of such failures in the future. Now, construction of the conservator tank. This is a cylindrical shaped oil container mounted on supporting structure on the roof of the transformer main tank. A short length pipeline from main transformer tank is projected inside the conservator from bottom portion. Head of the connected pipeline inside the conservator is thus to be fitted with a special type of cap which would have to prevent from entering oil sludge and sediment in the main tank from conservator end. Large inspection cover is provided on one side of the container to facilitate periodic maintenance and cleaning inside the conservator tank. Conservator tank is always be partly filled with transformer oil, and its main function is to provide adequate space for expansion as well as contraction of oil inside the transformer during running operation. Conservator tank signifies an important role in maintaining the dielectric fluid pressure inside the main tank during the optimum working conditions of the transformer. This is the main features of the conservator tank. So far, oil field transformer is concerned, the use of conservator has also to be greatly benefited to allow the main tank to be filled with dielectric fluid up to its cover, and that may facilitate to effect cover mounted bushings where to be required. The bushings typically made from porcelain or epoxy resin are mounted over the main tank and perfectly act as insulated barriers that contain the terminal that connects the current carrying conductor from an electrical network to the end of the transformer windings. Only for conservator type of electrical transformers operating above 500 kVA, a gas actuated relay or Buchholz relay is mounted on the pipe connecting the main tank and the conservator. In order to allow easy oil flow through the Buchholz relay, the pipeline where to install the relay is normally tilted at an angle of 5 degrees to the horizontal. To obtain optimum performance from a transformer of higher rating, that is 132 kV and above, then it is always be recommended on maintaining a high degree of dryness of the oil, typically less than 10 parts per million, 10 ppm by volume at 20 degrees centigrade. As the conservator has taken up all the expansion and contraction of the oil under variation of load, so the main tank oil is never be exposed to atmospheric air. However, comparatively very small amount of air is only coming in contact with the area of the oil in conservator. This has greatly benefited by causing possible reduction of rate of oxidation of the oil, and also would have to restrict the level of dissolved oxygen in the oil. Another perspective is that the formation of sludge is thus to be significantly reduced, and whatever be the sludge formed would have to be confined only within the conservator. For accumulation of sludge, that might be formed over a period of years by oxidation of oil. A possible oil sump is arranged within the conservator space just to avoid from choking with sludge. The oil pipeline which has to connect with the transformer main tank must be made to project through the bottom section of the conservator by again again I repeat, just to avoid from choking with sludge, the oil pipeline which has to connect with the transformer main tank must be made to project through the bottom section of the conservator by about 75 millimeter of length. See in figure 105. It is most important. That is, just to avoid from choking with sludge, the oil pipeline which has to connect with the transformer main tank must be made to project through the bottom section of the conservator by about 75 millimeter of length. See figure 105. A lockable drain valve is normally fitted at one end of the conservator bottom, and if necessary, the internals may be cleaned out. At one end face of the conservator is usually configured with a prismatic oil level gauge or a magnetic dial type gauge, that is emoji, which has to indicate the position of transformer insulating oil level in conservator. However, gauges must have to be mounted in a way which slightly tilted towards by an angle 10 degree to 15 degree so as to view the readings from plinth level. During the breathing cycle of a transformer below 132 kV, it is much crucial to restrict the level of moisture and to prevent atmospheric moisture from entering at the airpace above the conservator oil level. Total breathing process would have to be incorporated through a simple but effective protection device like the silica gel breather. Silica gel breather fixing pipeline has to connect with conservator from its top, and arrangement is such that must ensure that oil in no way would have to enter at silica gel breather line even at maximum operating level of transformer. Effectiveness of using breather must have to depend on the dryness of silica gel, as because it is strongly hygroscopic. Silica gel is basically colorless, amorphous silicon dioxide and has a gel-like to solid consistency. As a previous concept, the silica gel was usually impregnated with cobalt chloride, whose color would have become blue at dry state and changing to pink when completely saturated with moisture. But cobalt chloride has suspected to be carcinogenic and very toxic, and indicating silica gel with cobalt chloride is listed as a hazardous substance for disposal by the Europe Union. Presently, Sorbid orange, a biodegradable proprietary organic impregnant, is generally preferred as an indicating silica gel for moisture control, which is bright orange when at dry state and changing to translucent when wet. Presently, sorbit orange, a biodegradable proprietary organic impregnant, is generally preferred as an indicating silica gel for moisture control, which is bright orange when at dry state and changing to translucent when wet. Moisture saturated gel can be reactivated by means of drying it in an oven up to the color of the crystals, which will revert to their original color, bright orange, from translucent when wet. So, vent type conservator tank should have an adequate space to allow the expansion of the oil during high ambient temperatures and plays an important role in case of transformer having HV winding of less than 132 kV rating. Thus, basic design criteria for vent type conservator tank is thus vented to the atmosphere to balance the pressure changes during expansion and contraction of the oil by breathing the air in and out of the tank. As per IEC, the conservator design should be implemented by considering the oil level increment with temperature ranging from minus 25 degrees centigrade to plus 110 degrees centigrade. Conservator with breather type can be used for virtually any size of transformer, but that depends upon a number of factors such as dryness of the silica gel, the moisture content of the incoming air, and the ambient temperature. Since moisture is being a most significant element for degradation of normal insulation system, and any moisture which is taken in through breathing system during all the time that transformer is on load. So it is desirable to maintain the principle employed in the refrigeration type of breather. Again, I repeat, since moisture is being a most significant element for degradation of normal insulation system, and any moisture which is taken in through breathing system during oil and all the time of that the transformer is on load. So it is desirable to maintain the principle employed in the refrigeration type of breather. Incoming air before entering to the breather is thus to be passed through a low temperature chamber, which causes any water vapor present to be collected on the chamber walls. As because of thermosiphon action created between the air in the cooling region and that in the airspace of the conservator would have to create a continuous circulation, causing a process of continuous drying action takes place. Moisture trapped in insulation would also be dried up consequently with the prevailing system of refrigerant dryer unit. In very humid climate, as prevailing in many tropical countries, The refrigeration dryer type of breather is widely used at transformers of 275 kV and above. To entertain an optimum dryness of the oil for power transformer having HV winding of rating 132 kV and above, it is always be recommended for using Atmoseal type conservator tank. Atmoseal type conservator tank has a flexible bladder which acts as an air cell, and depending on the reflecting, that is swelling and deflecting of the air cell with the help of its breath, that would have to allow contraction and expansion of oil. Atmoseal type conservator tank. The air cell is made of high temperature resistant, that is 130 degrees centigrade NBR material, that is nitrile butadiene rubber NBR, reinforced with high strength nylon, that is polyamide fabric, and acts as a flexible separator while fitted inside the conservator reservoir. Outer side of the air cell is coated with black acrylonitrile butadiene rubber for providing better oil resistance. An air cell is specifically designed to act as a long-term airtight barrier so as to isolate transformer oil within a conservator tank from undesirable elements in the atmosphere, such as moisture, nitrogen, ozone, and oxygen. These barriers may also subject to reduced condensation and oxidation phenomena inside the transformer components, and would have to suppress gas bubble formation in the transformer oil. Air cell as floats in oil inside the conservator and be able to expand or contract with the help of breathing process through a flange placed in a specified location, thus allowing the air cell to compensate for oil displacement due to temperature variations in the transformer. Pressure of air inside the air cell should be maintained 1 psi, that is 0.070307 kg per centimeter square. A flange is inserted into a specific location of the air cell, which has to provide for allowing the usual air breathing process, which has made the system enable to compensate for all sorts of oil displacement due to temperature variations in the transformer. Oil also can be filled into the transformer tank without being exposed to the air. Since the insulating oil is completely isolated from the atmosphere by an air cell, and as the oil surface pressure is constantly maintained at the atmospheric pressure, so there would have been no possibility of the oil becoming supersaturated, and for which that would have to suppress forming of bubbles. Thus, high dielectric strength of the oil can be maintained for a extended period. It can suppress forming of bubbles. As per requirement of the consumer, a leakage detector of the airbag, also indicated as bladder failure relay can be mounted on top of the conservator for detecting air bubbles in the oil. However, this relay would have to serve as a backup protection to the Buchholz relay. See the diagram of Atmoseal type conservator tank. See, the pipe to connect with transformer main tank must be made to project through bottom section of the conservator by about 75 millimeter of length to avoid choking with sludge, oil sludge. The oil gauges tilted 10 to 15 degree angle. Air release flange, airtight oil filling port, flange to connect vacuum pump while transformer oil filling. While for transformer oil filling, this is the mechanical inspection for manhole. Air cell venting line, 3/4 to 1 inch dia. This is breather. See the air cell. Actual configuration of air cell and the conservator tank. Air cell, drain valve, connected main tank, float arm, breather type, planes to connect vacuum pump, airtight oil filling port. This is diagram of magnetic oil gauge. This is air cell failure relay. Now, we have to discuss diaphragm sealed conservator. A diaphragm is used as a barrier between transformer oil and atmospheric air. In this case, the conservator of transformer is made of two semicircular hubs as shown below. The diaphragm is held between the two hubs and is tightly bolted. The top of the diaphragm is open to atmospheric pressure through a silica gel breather or refrigeration type of breather. As oil expands and contracts and having the atmospheric pressure changes due to reflex and deflex of the diaphragm, which causes breather air, which causes breathe air in or out, keeping both air hub and transformer oil essentially be at atmospheric pressure. Position of the diaphragm is thereby indicated by the reading shown at the oil level indicator, that is magnetic oil gauge, which is not shown in the previous figure, which is functioning with the float arm of the subject float, is connected near center of the underside of the diaphragm. The soft diaphragm capsules are made up of high elastic coating fabrics, which has to vulcanize to a high temperature vacuum environment to prevent any sort of rupture during operational phase. An internal reinforcement structure has to be provided just at the junction point between the outer side of diaphragm capsule and the float itself as fixed for oil level indicator. That is, one reinforcement structure is required at the junction point of the connection of the float with diaphragm. See the drawing. See the diagram. One part of the compensation bladder is separated. This is a bolted one. The fabric reinforced structure is thus to be constructed with high performance polyamide wire, and the product must have to possess excellent permeability against oil, gas, moisture, and temperature. The diaphragm outer side coating should have a high resistance to transformer oil as employed, and internal surface should also have a high resistance to nitrogen and atmospheric corrosion reagents, including ozone. No possibility of leakage at the vulcanized flange interface must have to be ascertained during fixing. As the flexible compensating bladder provides an excellent barrier of contract and condensation of air and oil, so possibility of oxidation and hydrolysis of the oil can be readily restricted. Again, I repeat, as the flexible compensating bladder provides an excellent barrier of contact and condensation of air and oil, so possibility of oxidation and hydrolysis of the oil can be readily restricted. Points to be noted that the bladder failure relay is not needed for diaphragm type conservators. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage me to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want to know, then let me suggest in the comment section. Thank you. Thank you for patient hearing.